So let's talk about the previous laboratories about the Saliency maps and GradGAM of class activation maps using PyTorch and ResNet. So uh, the laboratory main objectives is we load the pre-trained ResNet 50, how images are pre-processed before entering the convolutional neural network, how to make predictions, how Saliency maps works, how GradCom works, and why GradCom is usually more interpretable than Saliency maps, and how Python hooks are used inside the GradCom. So first of all, why do we need visualization? Normally, convolutional neural network, like uh, we have the image, we perform convolutional network, and prediction. Example, we have the dog image, and we use the pre-trained model ResNet 50, and then we predict golden retriever, like we have the score of 99%. The problem is, how did the network know it was a dog? Did it use the ears, the nose, the fur, the background? So without visualization, we don't know. Visualization techniques answer what part of the image caused this prediction. What part of the image caused this prediction? So uh, let's load the pre-trained ResNet. So we have a TV model that ResNet 50, the model of it. Instead of training from the scratch, we load the pre-trained model. It already knows 1000 images classes. For example, dog, cat, airplane, car, elephant, and banana. Creating this model from scratch will take days or weeks. So we perform now the image processing. ResNet 50 expects 224 by 294 RGB, and we normalize it. So we perform we resize it to 224. We perform the 2 tensor. We normalize it. We perform the convolutional neural network. So we have the mean and standard deviation of the data. So we use the ImageNet statistics mean and standard deviation because ResNet 50 was trained this way. Every new image must be normalized the same way, otherwise performance drops. So next, prediction. So he performs the prediction, like we fed it in an image and perform a convolutional neural network. We have the 1000 logits and perform the softmax, and which is the highest probability that's we're chosen. Like for example, the logits dogs 0.96, the wolf is 0.2, fox is 0.1, horse is 0.1. Since the dog is the highest probability, therefore the prediction is dog. So here we go, we are in the Saliency maps. Now comes the interesting part. Instead of asking what class is this, we ask which pixels most affected this class. So the mathematical idea, normally you have the image, the convolutional neural network, and the output is dog score. And Saliency computes the gradients of dog score with respect to input pixels. So the gradient of the dog score with respect to the pixels. So yeah. So why gradients? Imagine changing one pixel slightly. If the prediction changes a lot, that pixel is important. If changing a pixel barely affects the prediction, it isn't important. The gradients measures this sensitivity. So large gradient means very important, and small gradient is not important. So the function compute Saliency map does the forward pass, predict class, and backpropagate. So we compute the rate of change of score with respect to pixels, like the absolute value, and have the maximum across RGB channels, normalize and displays the heat map. So why take the maximum over the RGB channels? Each pixel has RGB, each channel has its own gradients. Like for example, red gradient 0.2, green gradient is 5.8, blue gradient is 0.7. So the maximum is 5.8. Now each pixel has one importance value. So the result, we get something like white is very important and black is not important. where the brighter pixels influence prediction most. So, limitation of Saliency maps. Saliency is pixel level. That means millions of pixels and are considered independently. The results, lots of noise. An example, we have the dog. It becomes difficult to interpret. This is why GradCam became popular. So, instead of asking which pixels matter, the GradCam asks which feature maps matter. This is huge difference. Remember the CNN feature maps, the earlier layers is detect the edges, corners, textures, and the later layer is eyes, legs, wheels, faces, and the last layer, entire objects. GradCam works on these meaningful feature maps. So why this less convolutional layer? The reason is early layers is too much detail like edges, textures, but the last convolutional layers rich in semantic information like dog head, cat ears, cat wheels. After this layer, the network is mostly ready to classify. Therefore, it contains the most meaningful spatial information. Next is hooks. We use the hooks. Inside the class of GradCam, hooks are attached to the target convolutional layer. Two things are saved, forward hook and backward. So, forward hook stores feature maps. Example, we have the 2048 feature maps and each of it is 7 by 7. And backward hook stores the gradients. So this tells us which feature maps contributes most of the prediction. So what happens? We perform the forward pass with the image convolution neural network, and the last convolution layer receive the feature maps and the prediction, and perform the backward pass and save the gradients. So why gradients? Exactly the same idea as Saliency, but instead of pixels, we compute sensitivity of feature maps. Computing weights. So the average each feature maps gradient. Suppose feature map 1 have the average of gradients is 0.82 and feature map 2 is 0.01 and feature map 3 is 2.3. This become weights. So why we average it? Instead of examining every pixel inside feature map, we summarize its overall importance with a single number. So each feature map gets one weight. So we have the weighted feature maps. Now each feature map is multiplied by its weights. So like feature map A multiplied by its weight, feature map B multiplied by its own weights, and feature map C multiplied by its own weights. So feature map C contributes almost nothing because of its score like 0.0. So the feature map A dominates because it's the highest one. So sum them. Finally, weighted map 1 plus weighted maps 2, weighted map 3. So we produce the GradCam heat map. Exactly what we have discussed before. Like each feature map is multiplied by its importance weight. Then all weight feature maps are summed. So and then we apply the ReLU. This gives positive influences because GradCam wants the highest evidence supporting the predicted class. Negative values would represent evidence against that class, which will make visualization harder to interpret. Precise feature maps are 7 by 7. Original image is 24 by 24, 224 by 224. So the GradCam upsample 7 by 7 to 224. Now both images align. And finally we overlay like the original image plus the heat map. So we immediately see where the model was looking. Example, dog heat map mainly on face, ears, eyes instead of the grass. So the entire GradCam pipeline from the image and produce the rest at 50, perform the last convolution layer, save the feature maps, then prediction, then perform the backward, save the gradients, average the gradients, weights, multiply feature maps to the weights, we sum them, perform the ReLU, resize it, we overlaid it, and yeah, that's the GradCam heat map. So if you compare the Saliency maps and GradCam, the Saliency maps uses the input pixel gradients and GradCam uses gradients of feature maps. Saliency maps is very detailed, but the GradCam more semantic and easier to interpret. Saliency maps is often noisy. GradCam usually much cleaner. And Saliency map shows important pixels, and GradGam shows important regions. Saliency maps works directly on the input image, and GradGam works on the last convolutional layer. So the final key takeaway here, Saliency maps answers which individual pixels most influence the prediction. They compute the gradients of the class score with respect to the input pixels. The result is very detailed but often noisy. And GradGam answers which regions of the image did the CNN focus on. It, it uses last convolutional layers feature maps. Weight them according to the average gradients for the target class. Sums the weighted maps, applies the value, and upsamples the results of the original image size. This produces a much more intuitive localization heat map. And then both techniques rely on backpropagation, but they visualize different things. Silence works at pixel level, but while your GradGam works at the high level feature map, which is why GradGam generally preferred for interpreting CNN decisions.